So here we go with example 3 from chapter 8.1. So let's begin with the usual routine, read through the questions, pick out the key information. So an ice skater is skating on a large flat ice rink at time t equals 0. The skater is at a fixed point O, so it's at the origin. It's travelling with a speed 2.4 I and negative 0.6 j meters per second. At time t equals 20, the skater is travelling with a velocity minus 5.6 I plus 3.4 j meters per second. Then we get relative to O, the skater has a position vector S at time t. The skater has a particle with constant acceleration. So already we know that this is likely to be a SUVAT kind of question. Okay, part A then. What have we got to do? The acceleration of the ice skater. So, part A. It's constant acceleration. So we can start thinking about SUVAT. And what do we know? At t equals 0, the velocity is 2.4. U is equal to 2.4 and negative 0.6 meters per second. When t equals 20, v is equal to minus or negative 5.6 and 3.4 meters per second. And the question asks for the acceleration. So we can go into our usual state, sub, solve kind of approach. V, U, A and T. So V is equal to U plus AT. Squiggles for the V, U, A and A because they're vectors. Nothing, no squiggle for the T because it's a scalar. Substitute in the values, negative 5.6 and 3.4 equals U, which is 2.4 negative 0.6 plus A, which we're trying to find, times 20. Okay, now we've got to make A the subject, so we're going to go subtract the U vector. So we're going to get from here, these two are going to give us minus or negative 5.6 minus 2.4 is negative 8. Then we're going to look at here, the 3.4, add the negative or add the 0.6 onto both sides. So we're going to get 3.4 plus 0.6 is 4. Is equal to 20A. Okay, so 3.4 plus 0.6 gave us the 4. So divide both sides by 20. So negative 8 over 20 is minus 4 over 10, which is negative 0.4. 4 divided by 20 is a fifth, which is 0.2. Gone back to decimals because that was the form of the question. And it was an IJ notation, the form of the question, so we're going to finally write our answer out then as A is equal to negative 0.4 I plus 0.2 J, and its acceleration, so it's meters per second squared. Just try and squeeze that on. Okay, so B. Find an expression for S in terms of T. So, part B. We've got the same starting information as we had before. U. So, again, we're in a constant acceleration context. U is t equal to 2.4, negative 0.6. T. We want an expression in terms of t, so we don't actually know t's value. We know v is equal to minus 5.6 and 3.4. And we've been asked to find S. So it's better to use the previous information, things that we've already been given, rather than something we have worked out. So use info from the question, use info from question rather than calculated. Oh, hang on, there's a mistake here, isn't there? Because this V was when t was equal to 20, so it's not known. Therefore, it's not known. Okay, come back over here. Use info from question rather than calculated values if possible. But in this case, because V is not known, we're going to have to use our calculated value, which was A. And that is negative 0.4, 0.2. So come back over here and let's have a look at what values we have. What else we've got? We've got U, we've got T. We haven't got V because that was the velocity at the end. S is what we're trying to find in terms of T, and we've got the acceleration. So S, U, A and T. Our state is going to be S equals UT plus a half AT squared. Which one of those needs squiggles? You're right, I hope. S, U and A are the vectors and the T doesn't. So S is what we're trying to find. U is 2.4, negative 0.6 T plus a half A, which is negative 0.4, 0.2 T squared. So now we want to convert back to IGA notation. So S is equal to, let's look at what we've got for I's. Well, I, we've got that bit, half T squared times the negative 0.4. So we're going to have S equals 2.4 T. Negative 0.4 times a half is negative 0.2. And then T squared. So that gives us that. And that is the I component. We're also going to have a J component. I'm going to have to write a little bit smaller here to fit this in, I suspect. So the J component now is going to come from here. Again the T, again the half, the 0.2 for the J, and again the T squared. So we get negative 0.6 T. A half times 0.2 is 0.1, and that's plus 0.1 T squared, and that is the, and it won't quite fit in, I don't think, yeah, the J component. So that is the answer. We've got S in terms of T as required. The only other thing I might write on the end of there is that it's meters to keep the units correct within the question. Okay, part C. The time at which the skater is directly northeast of O. So, north, east, and it's got to be northeast. So to be northeast of O, to be northeast, what do we know? Well, that angle's 45 degrees, so this distance here, the easterly distance, is the same as the northerly distance. They must be equal. Yeah, to be northeast, the I component must equal the J component. So our I component is what? 2.4t minus 0.2t squared must equal my J component, negative 0.6t plus 0.1t squared. So if we just went back and did the colour coding, it's that bit, that's the J component, and that's the I component, and they are equal. Okay, if we look at that, we can see what kind of equation we've got. And it looks a bit like a quadratic. And we like our quadratics to be quadratic positive equal to 0. So no need to change outside our usual routines just because it's a mechanic question. So we get 0 equals, add the 0.2t squared across to get 0.3t squared, subtract the 2.4t, so we get minus 3t. What's common? T. So 0.3t minus 3. Therefore, t equals 0 or t equals 10. And check back at the question. The time at which the skater is directly northeast, it's got to be t equals 10. At t equals 0, it was at the origin. At origin, therefore our answer is t equals 10. Okay, so we've now done parts A, part B, part C, so we're on to the last part. A second skater travels so that she has a position vector r, 1.1t and minus 6j relative to O at time t. Show that two skaters will meet. So part D. R. This second skater had a position 1.1t minus 6. 1.1t minus 6, and which directions was it in? The J component. So, what direction is R travelling in? So the second skater is travelling north. Now, how did I know that? Right. Well, since the I component doesn't appear in the equation, so it must equal 0. So it's not just travelling north, it is actually due north of the origin. So the second skater, therefore the second skater is due north of the origin. So that's the key into the question. So if we know that the second skater is only travelling due north, we've got to think of this as when is the first skater due north? So therefore we're going to find when first skater is due north, and see if their position is the same at this time, and see if their position is the same at this time. So first we're going to think about the first skater, and the I component must be 0. Due north of O when I component equals 0. So let's go back to this, and the equation is 2.4t minus 0.t squared. That's the bit that's highlighted green here that we're looking at. Yeah, that bit there, because we want that I component to be 0. So 2.4t minus 0.2t squared. I think it was, yes, must equal 0. Okay, well, take the 0.2t out as a factor. That will leave 12 minus t equals 0. So t equals 0, well, that's when it starts at the origin, or when t equals 12. So at t equal 12, we need the position. So at t equal 12, S is equal to, and we've got an equation here, well, we know that's going to come out to 0, so let's just think about the J component. Only consider J, because we know that the I component is 0, because we've already worked that out. So considering the J component, we're going to get, well, that's this bit highlighted in pink, negative 0.6t negative 0.6t, which is 12, and then plus 0.1t squared, plus 0.1t squared, which is 12. So negative 0.6 times 12 is negative 7.2 plus 14.4. 12 squared is 144 times a tenth. So that's going to be 7.2 minus 7.2, 14.4 is 7.2 meters. Okay, that was for S. Now we've got to consider R. So R. Again, I don't need the squiggle because we're just working on that J component. So R was equal to 1.1. So it equals 1.1 times T, which is 12, minus 6. So I'm going to get 12, 13.2 minus 6, lucky days, 7.2 meters. Therefore, they are at the same position at 12 seconds. Therefore, in the same place when T equals 12. Now, let's go back and check we've actually answered the question that was asked. Show that the two skaters will meet. So it doesn't ask for the time or the position particularly, but we have shown that they will collide. Okay, last thing to do then is set homework attention.